This is Sami Al-Alwani. This is a lecture about DC to DC converters, or what we call it, choppers. And it's like when we have a battery, a DC source, and then connect it to DC to DC converter, and then we have the resistive load. So these converters are used to change the average value of the DC current by using semiconductor power electronics devices. And the DC to DC converters are categorized into three categories: step down the voltage of the source, which is called buck converters, or step up the voltage of the DC supply, and this is called post converter, or step up and down the voltage of the DC supply, and it's called buck post converter. Or it can be categorized according to isolated or non-isolated DC to DC converter. So we have non-isolated, and this is meaning that the DC source is directly connected to the power electronics switches, like these three types. Or isolated DC to DC converters, and these are called has like too many types, like for example flyback converter, DC to DC converter, or forward converters, so on. So we will go through all these types in this chapter. So the first thing I'm going to talk about here is I will give an example of the DC to DC converter. If we have a DC source, let's say 10 volt, and then I have a load which is 5 ohms, and I want 5 volts across its terminal. So I have to put a 5 ohm resistor here to like divide the voltage, like voltage division rule. So I will have here 5 volt and here 5 volts, and the current is 1 amps. So the efficiency of this system is 50%. So 50% of the energy is reaching the load, while 50% of the energy is dissipated as heat here. So how we can use power electronics to improve the efficiency of the system? As we know that the nature of the supply voltage is DC, means that it's continuous over time. What if I applied like a switch here, and the switch has a very high switching frequency, meaning that it will turn on and off for each period. So let's say the voltage will become across the resistor for 50% of the cycle, and on in 50% and off for the other 50%. So we call this the period. Then it continues in the same manner, 50% on and 50% off. In this way, the voltage that appears across the resistor, if this is 10 volt, this is 5 volt, this is 0, this is 5, the voltage that appears across the load will become, instead of 10, 5 volt, and little energy will be dissipated as heat during the switching time of the semiconductor device, and this will account like 5% or less. So in this way we improved the efficiency tremendously by using power electronic device. So now I will start with the first type of DC to DC converter, which is the buck converter. The buck converter is a step down converter. It means that the DC voltage level of the supply will be reduced on the load side. So let's say this is the circuit diagram. We have the DC source, and I call it VN. Then I have here, for example, the IGBT, which is the switch. Then a diode is connected likewise, and then I will have an inductor and a capacitor in parallel with the load resistance. So this is the load resistance, this is the cap, this is the L of the converter, and this is the diode. This is the switch. Here we will have the output voltage. So let's analyze this circuit. First of all, I will define the duty cycle, which is the time at which the switch is on, and we call it on time of the switch, S, W. Okay. Over the period is equal to T on time, the on time of the switch, divided by T on plus T off. So if we have a switch, the on and off times of the switch will be in this manner. This is T on, this is T, the period, so this is T off. So the duty cycle is the on time of the switch, which is this one, divided by the whole period as a function of time. So this will be T on over T. Now for this converter, I will write some assumption that will make the analysis of this circuit is pretty easy. Assumption number one, that we are working on steady state. Number two, IL is continuous, meaning that the current that is flowing through the inductor here, IL, is continuous. Number three, the capacitance of the capacitor is very high, or high enough to hold the output voltage across the load as constant voltage, meaning that there is no peak-to-peak ripple, which is equal to 0. Number four, the switch close at t equal to dt. As we said here, we have T on and T. T is the period, T on is the time at which the switch will turn off. So this T on is the duty cycle multiplied by the period. So I wrote it here. And the switch open at T equal to 1 minus D multiplied by T. So so how did we find that? This is actually T off, is the time at which the switch is open. So if we looked here, T off is actually T, which is the total period, minus dt, which is the time at which the switch is closed. So the total duration of the period minus T on, it will give me T off. So this is where I got this one. So now the last assumption is that we have ideal components in the circuits, meaning that the losses into the capacitor, the losses into the inductor, and the losses into the switch due to the switching of the switch, all of them equal to 0, meaning that these are ideal components. We don't have any losses into the system. So now I will start analyzing the circuits after these assumptions. So the first mode number 1, happens when the switch is closed. And when the switch is closed, the diode will act as an open switch, meaning that there will be a current flowing from the source, DC source, through the current to the output resistor. So the current flowing through the inductor will start to charge the inductor and the capacitor and supply the load current. When this is mode number 2, it happens when the switch is open, and when the switch is open, the diode will turn on due to the energy stored into the inductor. So the inductor current will force the diode to turn on after the switch is open. So now I will draw some waveforms that describes the behavior of the system during these two modes. So the inductor current, let's say that the inductor current starts from a minimum value after steady state is achieved, start from minimum value up to a maximum value. So during the first switching time dt, let's say this is t, during the first mode the inductor current is charged by the source current. So it will start from a minimum value until the switch is open. Then the inductor will start to discharge through the load resistance, meaning that its value will start to decline until time t, the period, and it reaches a minimum current again. So this is the maximum value of the current, and it happens at time dt. Now, what happens to the load current, IR, since these components are ideal, meaning that IR will equal to IL. So they have the same waveform. So we have like a peak-to-peak ripple between the minimum and the maximum value in the inductor current, and this is called delta IL. So if I want to analyze the circuit, first, in the first mode, if I apply Kirchhoff law to find the IL or V output, so I will have a voltage drop across the inductor, a voltage drop across the load, and an input voltage. So the sum of these three voltages will equal to 0. So the sum of the voltage source equal to the sum of the voltage drop. So V input is equal to VL plus V output. So this will equal to V input, VL, the inductor voltage, is equal to V input minus V output. So now VL is equal to V input minus V output, which is equal to, and we know that VL is also equal to L DIL over dt. So I will substitute these two equations and make them equal together. So it's L DIL over dt. Now from graph, IL at any time is equal to the minimum current, which is the initial value here, plus the V input minus V output over L multiplied by the time t. So I just divided by L and multiplied it by t. So if I said IL at time dt is equal to I minimum plus V input minus V output divided by L, instead of t I put dt. So as we can say, this is the maximum value, since the maximum value of the current happens at dt. So IL at time dt is the maximum value current, which is equal to the minimum value current plus V input minus V output over L dt. This is equation number 1. I can also find this one in a different way. After using this equation, I can say Vn minus V out divided by L is equal to DIL is the maximum value minus the minimum value divided by the time dt minus 0. I just used this one. I maximum minus I minimum divided by dt minus 0. So I get V input minus V output over L equal to I max minus I min divided by dt. So multiply this here. So I get I max equal to I min plus V input minus V output over L dt, which is the same equation. Now, during the second mode, when the switch is open and the current starts to decline until it reaches time t. So if I want to find the voltage current relationship, this is VL, this is V out, so I can say VL is equal to minus V out. So VL is equal to L di L over dt. So minus V out is equal to L di L over dt. And as we know, in this second mode, the current starts from dt and end at t, start from maximum value and end up to minimum value. So minus V out over L is equal to the minimum value minus the maximum value of the current divided by t minus dt. So I minimum is equal to minus V out over L multiplied by t minus dt plus I max. So I min, I rearrange the equation to I max minus V out over L 1 minus d multiplied by t. So this is equation number 2. And if I want to find the peak-to-peak level of the current, which is I max minus I min, I will get that delta IL, put it in 1. So I will go to equation number 1, which is this one. I will substitute I max with this one. So I min will go with I min, so I will left with Vn minus V out over L dt. IL also equal to V out over L 1 minus d multiplied by t. So if since delta L is equal to this one and this one, we can write it in this way: V input minus V output over L dt is equal to V out over L 1 minus d multiplied by t. So the t goes with the t, and if we rearrange this equation, we will get that V out over Vn is equal to D, which is the duty cycle. So the input-output relationship is like V output will equal to V input multiplied by D. So this is the input-output relationship between the input voltage and the output voltage. Now, if I want to find the average value of the current, as we said, if this is like the switching frequency of this converter, the IL, the current, we're gonna be like that, increasing, decreasing, increasing, decreasing. Here it's dt, so it has like a minimum value and a maximum value. And if we want to find the average value of the current that's flowing through the inductor, and it's actually equal to the current that is flowing through the resistor, which is equal to V output over R. And we know that IR is equal to, or the average value of the current across the resistor is Imax plus Imin divided by 2. So we say Imax is equal to, if I want to find Imax, is equal to IR delta IL over 2, and Imin is equal to the resistive current plus minus delta IL over 2. So I will use these two equations and I substitute the value of IR. So Imax will equal to V out over R minus delta IL. I will take this one, V out over L, 1 minus D multiplied by T multiplied by 2. Then Imin is plus, Imin is V out over R minus V out over 2L multiplied by 1 minus D multiplied by T. So I take VR as a common factor. I will get that Imax is equal to V out multiplied by 1 over R minus, and I will replace T with 1 over F, which is the switching frequency, 1 over 2L multiplied by F, 1 minus D. So this is the equation that we will be using to find the maximum value current. Also, Imin is plus. Imin is equal to V out 1 over R minus 1 over 2LF 1 minus D, and this is equation number 2 to find the minimum current. This is in CCM, meaning that when Imin is greater than 0, the converter is operating under CCM, continuous current mode. But when Imin is equal to 0, this is called DCM, discontinuous current mode, meaning that the current will behave like a triangular waveform. So I want to find the value of L that will make the current operating under CCM. So I will write the equation for I min, which is equal to V out 1 over R minus 1 minus D divided by 2LF. So this is 0 equal to V out 1 over R minus 1 minus D over 2LF. VL will go since it's a constant, and I will find that L will equal to 1 minus D multiplied by R divided by 2F. So when we increase from this equation, increasing the frequency will decrease the value of the inductor being used into the converter. Also, the resistive value of the load will affect the continuity of the current. So if we have variable load, okay, so we have like the load on the other side of the converter is between minimum value and the maximum value, we will take the maximum value of the resistor, because we will find the maximum value of the inductor that will make the current all the time continuous. Then this inductor, or the minimum inductor needed to make the current continuous, I will multiply it by 1.2 multiplied by L for safety reasons. So always we will get an inductor that is greater than 1 minus D divided by 2F multiplied by R. So we know how to design the inductor of the converter that will make the current always continuous. Now let's find C, the capacitor that will minimize the peak-to-peak ripple of the output voltage to a certain value. The current that is flowing into the capacitor will start from negative, reaches a maximum value, and return back to its negative value at time t. This happens the peak value at dt. So we have delta IL here, the same peak-to-peak ripple of the inductor current. The voltage across the capacitor as a function of time. If this is the output voltage, it will behave like so. This is T, this is dt. So the average value of the voltage here is equal to 0. So this is delta V out. Now since the voltage here depends on the capacitor, depends on the current that is flowing through the capacitor, I have to find the charge, or delta Q, during the charging period. So this will give us like the peak-to-peak ripple of the voltage. So as we see here, the charging time is half of the cycle, means here we have some time and here we have some times where the capacitor is discharging, but the charging time is the period divided by 2, and we know that delta Q is equal to C multiplied by delta VC. So if I want to find the delta Q, I want to find the area that is here. So it will be, it's a triangle, so it's half multiplied by base multiplied by height. So it will be half multiplied by base, which is T over 2, multiplied by height. The height here is delta IL divided by 2. So since all of this is delta IL, so half of it is delta IL over 2. So I will delta IL over 2. So I will get T multiplied by delta IL divided by 8. So now delta VC, which is equal to delta V out, is equal to delta Q over C. So delta V out is equal to delta Q. I will substitute its value. So it's T delta IL divided by 8 multiplied by C. We know that T is 1 over F, switching frequency. And also we know that delta IL is V out divided by L1 minus D multiplied by T. So I will substitute these two, and I will get delta V out is equal to V out over 8 multiplied by L multiplied by C multiplied by F multiplied by 1 minus D. And we already have another T here, which is, we have a T here and a T here, and when we multiply them it becomes square, so it's F square. We will have square here. So delta V out over V out is equal to 1 minus D divided by 8 LC F square. This is how to find the peak-to-peak ripple, and we can see that it's not a function of R. It depends highly on the frequency, depends on the inductor and also on the capacitor. So if I want to find the minimum C, that will gives me a certain level of peak-to-peak ripple in the output voltage. I will get that C equal to V out divided by delta V out multiplied by 1 minus D over 8LF square. And then I multiplied the minimum C required, multiplied 1.2 by this C. If I want to look at the input current, that is the current being drawn from the supply, for ideal converter, P input is equal to P output, and we know that P input is V input multiplied by the average value of the input current is equal to V output multiplied by IR. So V output or V input, we know it's equal to I input divided by IR, which is equal to D, meaning that the waveform of the input current is discontinuous in nature. This is the input current from the battery, so this is discontinuous current, and this is a disadvantage. Next, I will solve an example. So stay tuned please to my lectures.